Hi everyone, welcome to the afternoon session of Highlights. This session is going to be about vector addition systems and the Skolem problem. And the first paper the first presentation is something probably many of you have already heard about. It's a very nice result. And the talk is going to be given by Henry.
Thank you very much. Good afternoon. Hi. It's my pleasure today to talk about vector addition systems with states, and I'm going to talk about the coverability problem. I'm a PhD student from the University of Warwick, and this is joint work with four wonderful co-authors, Marvin Künnemann, Filip Mazowiecki, Lia Schütze, and Karol Węgrzycki. I'm well aware that some of the audience probably aren't that familiar with VASS, let alone coverability, let alone anything to do with Rackoffs, so I'll give a warm introduction, don't worry. I am also aware that some of the audience are already very familiar with these things, so don't worry as well. I should say thank you very much for choosing to attend my talk. I hope you enjoy. Right. So first I'll go through a little example. Vector addition systems with states consist of, or you can see them consisting of directed graphs with vector weights. These vectors contain integers. In this case, I've got two-dimensional vectors. And in VASS, a run consists of a sequence of configurations, and a configuration is a pair of natural numbers that are the counter values and a state. So the counters can't take negative values, but they can be updated by negative values. And I can ask a question like, oh, I should probably say first that as the session name indicates, vector addition systems is shortened to VASS. So when I say VASS, that's what I'm referring to. And I can ask this instance of coverability. It's a question from A, can I reach G via a path that's never negative? So I need to make sure that my sum remains above 0 at all times. So I'll start A with 0 and 0. And notice that I can't immediately go to C because I'd get -7 on the first component, and that's negative, that's not allowed. So I can go down to B and I'll get 2 and 0. From here I can now get to C with 5 and 8. And from C I can get to E with 3 and 10, and from E I can go down to D with 7 and 5. But notice now at D, I can't go directly to G, either via F or directly. I'm going to run out of value on the second component, I'm going to go negative. So I'm going to have to do some thinking. It's like a bit of a challenging problem. Okay, that's a great idea, that's a good find. There's a good cycle there with +1 on the first component and +10 on the second. I can run this cycle as many times as I like, and I'll get my sums as high as I can. And now, once I've taken this, in this case 2 times, but as many times as I liked, I'm no longer scared of the negative updates that follow because, well, my values can be as high as I liked, and I can now go to G directly. And so this is a positive instance of coverability, in this case in two-dimensional vector addition systems with states. I want to make the problem more challenging, so I add more components. And coverability in VASS is just the problem from a state P, can I reach a state Q via a path that's never negative on all components throughout? Yeah, this problem's quite challenging. I won't bore you with any more examples, but I'll quickly motivate the problem, like why study coverability in vector addition systems. So I'll touch on 4 things very quickly. The first is that you can model discrete resource management problems. Like imagine you have a hybrid car, maybe it has a battery and a fuel cell. If you know the cost of every road, how much battery it uses and how much fuel it uses, you can then ask a question like coverability, which is from my current location, can I get to some destination, right? Via some maybe crazy means of taking some strange meandering paths to charge up your battery and maintain fuel carefully. VASS are also equivalent to Petri nets, a popular model that were originally designed for modeling physical and chemical processes, but now I guess more for business processes and concurrent systems. And kind of on this line, coverability can be used to test safety. If you can define the set of states of a program and you can define the set of actions of a program, a coverability-like question asks, is there a sequence of actions that leads me to some state? If you define that to be a bad state, then you can ask for coverability, and a positive instance is indicating that your system is perhaps unsafe. And finally, just to touch on related problems, you might care for the unboundedness problem, which asks, from a given state, can I reach an unbounded number of configurations? This is very closely related to coverability, and I think the following ideas will be useful for studying unboundedness. There's reachability, which is fussier than coverability. Instead of just getting to a state, you'd like to get to a state perhaps with all zeros on all components or some specific values. It's much harder. And then perhaps more historically relevant is this problem of the uniform word problem for semi-groups. So yeah, that was just a light motivation. To give context to what our work was about, I'm going to have to give you a brief history. But before I give you a brief history, I'm going to have to define how to measure the size of these instances. So I'm going to reserve 2 letters, D for dimension, that's the number of components that I write down on every edge, and N the size of the thing encoded in unary. You can just think of this as adding the number of states plus the absolute value of every number you see on every vector. Okay, keep that in mind, or you don't have to, it's at the bottom of the slide. The first thing, already in 1976, Richard Lipton was able to show that coverability requires exponential space. You see this 2 to the d times log of the size of the machine. The idea goes roughly by finding hard instances that have extremely long minimal runs that witness coverability, doubly exponentially long, in fact. Appropriately, the examples that Lipton found are now known as Lipton's construction. And just 2 years later, Rackoff was able to argue that, well, you can decide coverability in VASS using exponential space. And the idea is complementary. You can argue that there are always doubly exponentially long runs that witness coverability, no matter what instance you ask for. So you might take a kind of distant look at this and go like, oh, we're done, right? Because this is exponential space complete, right? I've got an exponential space upper bound and I've got an exponential space lower bound. But there's a little gap between the two. And that's exactly what Mayr and Meyer asked in 1982. They saw this gap and they asked it as, well, they say an open problem, but I don't really see a question mark. It's more like an open command, like improve these bounds. I should probably say, I don't think this slide would be complete without mentioning a lovely piece of work by Rosier and Yen, which took a much more refined approach to analyzing VASS. That's why we have multiple parameters. The original work by Lipton and Rackoff just measured the instances as in like one unit. And they improved these bounds slightly in 1985 as well. Okay, so yeah, these theorem statements are really thanks to Lipton, Rackoff, Rosier, and Yen. Okay, so our main contribution is, well, in the title, it's improving Rackoff's upper bound, so we're probably going to shave off that log factor that sits in the double exponential. Indeed, that's what we do. Coverability in VASS is always witnessed by doubly exponential runs, but they're n to the 2 to the d, not n to the 2 to the d log d. And our approach is really the same as Rackoff's. There's nothing particularly scary about our approach, but we have to be very careful about what we define by our counter value bounds. So, like, what is Rackoff's very distant approach, or very distant sketch of this is, imagine you pick some astronomically large value to bound the counters, right? So I've got this green shaded region. If I ever see a configuration that jumps outside this region, then I know that at least one of my counters has exceeded some extremely large value. And at that point, I can effectively forget about it. It's so large that all the future negative updates it receives are kind of irrelevant, and I will always be able to cover that component. Kind of like we saw in the example earlier, once you've taken this cycle loads of times, your values are so high that you can kind of forget about them. Our approach is the same, but we have a new definition of what we consider to be thin configurations. We bound the largest component by the same value that Rackoff chooses, but we bound the second largest component by something a bit smaller and the third largest component by something a bit smaller. And we argue the same thing. If you ever leave this thin space of configurations, then you can do induction and shorten the run. Okay, but what does this shape even look like in higher than 2 dimensions? So I have a nice analogy. Imagine a shoebox. A shoebox is wider than it is deeper, and it's deeper than it is taller, like a cuboid of side lengths 3, 2, and 1. Now imagine all the 6 orientations of arranging your shoebox into like the corner of a room, like into an axis. And we just union this thing, and that's what we call thin configurations. Here's one I made earlier. So it was a gift from a friend at Warwick. They made this, so thank you, Alex. And it really shows you how much space we save over the cube that contains this shape. It gives you the kind of the difference between what Rackoff wrote down and what we've written down. Okay, I'm now going to conclude with our contributions. I know it's a short talk. So the first thing is indeed, like I've said, that we improve on Rackoff's by giving a double exponential but lower upper bound. This can be used to derive an exponential space algorithm that matches Lipton's lower bound. This can also be used to derive a double exponential time algorithm for deciding coverability by just doing BFS over the space of bounded configurations. Our second contribution is a matching conditional lower bound. So we use the exponential time hypothesis to argue that there are no truly sub-double exponential time algorithms for coverability in VASS. And this argues that the time algorithm that's awfully simple is conditionally optimal. Our third contribution is that when you've got dimension 2, like the example I showed you at the very beginning, that you cannot solve coverability in truly subquadratic time if you assume the k-cycle hypothesis, which asks whether you can find a cycle of length k in a directed graph. And finally, if you consider linearly bounded VASS, which I won't define now, but please do come and ask me afterwards, we have a lower bound based on the hyperclique hypothesis that is nearly optimal. Okay, I've made a poster, I should say, and I've got a little subsection of my poster devoted to each of these sections. So if you're curious about any of them, come and find me. I should be hanging around my poster for at least the remainder of the day. And yeah, thank you very much for your attention.